All right, good morning. So we'll get started, even though there's only 3 of us here. So in the last lecture, we were talking about polymorphism, well, this is all part of inheritance. And so remember in the last class, I told you what polymorphism was. It's I guess it's the ability of an object to have more than one type. And so in Java, remember that all of the types of the objects include its declared type. So the type that the class that it's defined in, all of its ancestor classes, and all of its interfaces. And so when you make a variable of some type, in this case counter, the type of the variable that when you declare it is called the declared type of the variable. And remember, it's the declared type of the variable that determines what operations you can perform with the variable. So obj, its declared type is object. And so the only thing that you can do with obj is call the big O object methods. Even though obj is an array list, you're not allowed to use any of the array list methods here because you've stated or declared that the type of obj is actually big O object. So for example, you can call toString or equals or hash code, but you can't call one of the list methods here. Okay, what about the thing on the right-hand side? So when you make an actual object, so here we're making a stopping counter, right? And we're going to store that in C, whose declared type is counter. The type on the right-hand side is the runtime type or the actual type. So in this case, the runtime type of C is stopping counter, right? Its declared type is plain old counter. It's the runtime type that determines which version of the method actually gets called when you use that variable. So for methods, this is only the non-static methods that count here. Static methods are handled differently. Okay. So for example, here, obj is declared. Sorry, the declared type of obj is big O object. Its actual type is counter. So when you use obj to call toString, you get the counter version of toString, right? Because it's the runtime type that determines which version of the method that you get. Right. So the runtime method, the runtime type of obj is counter, so we get the counter version of toString. Right. We're allowed to call it toString because the declared type object includes the method toString. So when you override a method in your class, this is the reason why you're doing it. You want that object to have a specialized version of the method that you've overridden. Right. So here we want to replace the version of toString that we got from obj so that it behaves the way we want it to when we use a counter. And so that print method, this particular print method, which takes in an object of type big O object. This will print any object in Java, right? Because everything is substitutable for big O object, right? Or every object in Java includes as one of its types big O object, right? So can I call toString on this object here? The answer is yes. Which version of toString do you get? Well, it depends on the actual object that's passed in to the method. Right. So if you use a string and print the string, you get the string version of toString. If you make a list and you print the list, you get the array list version of toString. And if I make a date and pass that to print, you get the date version of toString. Right. So again, the runtime type, so the type on the right-hand side, determines which version of the method that you get when you use that object to call a method. All right, so there's something funny about that code that I just showed you a second ago. So you go back and look at this class here. If you compile this in Eclipse or whatever, use the Java compiler to compile this, the compiler will compile this happily. In other words, it doesn't complain when you try to compile this code, which is funny because to figure out what method to call here, right, it needs to know what is the actual type of obj when the method is called. Okay. So the compiler can't actually determine which version of toString gets called when someone uses print. right? But this program compiles and runs just fine. Right? And so what does that mean? It means the actual version of toString that gets called can't be determined until you actually write a program and run it. Right? So you write a complete program, you run it, and then when you run the program, that's when which version of toString can be determined. Right? And so this is very different than all of the other method calls that we've been using so far in the course. Right? So far in the course, we've only cared about the type on the left-hand side. Right? So we've only cared about the declare type. Right? But now, when as soon as polymorphism is involved, or as soon as substitutability becomes involved, right? You now have this issue where the actual method that is called isn't determined until runtime. And so that has a special term that's called dynamic dispatch or late binding. These both mean the same thing, right? Dynamic meaning it happens at runtime and not at compile time, right? Dispatch meaning which method actually gets called, right? Late binding means the same thing. So late means at runtime, binding means which method actually gets called when the method is run. So that print example, it looks trivial, and it kind of is, right? But that illustrates the power of polymorphism. Oops, sorry. Right. So the programmer is able to write methods using an interface of the ancestor type. Right. So here we can write a method knowing only what big O object says it can do. Right. And now that method works for any object that you pass into it. Right. So for anything that's substitutable for big O object, this method does what it says it does. Right. Which is a very, very powerful idea. Right. Someone can write code using a superclass, and anybody else can create a subclass and run that same code, and it should work properly. Okay. So for example, if you look in the class collections, right, so remember this is the utility class where that operates on lists and sets. Right. When you look at the collection, wrong link. This should be an S. Sorry. So when you look at the signature of the methods, right, none of them say list. Well, not none of them. Many of them don't say list or set, right? So for example, add all just says collection, right? It adds all of these elements to the collection C, right? What type of collection? It doesn't matter, right? It doesn't matter if it's a list or a set. It doesn't matter if it's an array list or a tree set, right? This method just works, right? So someone can create this method and everybody else can use it. And whoever's using it doesn't care whether you're passing in a set, a set, a list, or any particular kind of set or list. All right. Now, to make this all work, there are some considerations that the programmer has to keep in mind. Right. And so this, it's called inheritance part 3, but this is really all about substitutability. Right. So what does it mean for one class to be substitutable for another? And so someone actually figured out what this is supposed to mean. So this was Dr. Barbara Liskov. She's still alive, as far as I know. Her and her graduate student came up with what's called the Liskov substitution principle. There is a formal definition for this. So if you go and look in the notebooks for the course, there's a notebook called Substitutability. There is a formal definition there. You can also Google it. It's a well-known principle in object-oriented programming. So basically what this thing says is that a subclass object must behave the same as objects of their supertype. Right? So for example, a string must behave like a big O object. Right? Or a stopping counter must behave in a way that's compatible with a regular counter. So the problem with this is that your programming language can't really help you ensure that this is true. So your compiler helps you a lot, right? It can read your program. It can tell you whether your program is syntactically correct. What your compiler and what most programming tools can't do is they can't tell you if your inheritance hierarchy is correctly following this principle. So if you do ensure that your subclass objects behave the same as objects of the supertype, then that is what allows programmers to write code according to the contracts of the superclass, right? And now the same code is also correct for all subclass objects, right? So you can write some code using only your superclass, using only the methods or the contracts from your superclass, right? Anybody else can come along later on, make a subclass, and then call your code, and everything should work the way it's supposed to. As long as you've paid attention to ensure that Liskov substitutability applies. Okay, so what do you have to pay attention to? So remember, way back in like week 3 or 4, I told you about class invariants. We told you about method preconditions and postconditions, right? These all now interact when you are implementing inheritance, right? So if your superclass has a class invariant, right, then that invariant applies to all of its descendant classes, right? Because, right, your subclasses must behave the same as objects of their supertype, right? The superclass has a class invariant, your subclass gets the same, gets a compatible invariant. Right. Oops, right. So if your subclass fails to support the invariant of the superclasses or of its ancestor classes, right, then anybody who wrote code using only the ancestor class contracts, they can no longer guarantee that code is correct. Okay, so here we have an example using counter. Right, so remember, counter has a class invariant, right? Its invariant is the value of the counter is never negative. So someone can come along, look at the counter contract and say, oh, okay, so I can write this method called isOdd, right? It takes in any counter, right? Not just a plain old counter, it can take in a stopping counter or anything else, right? And this code should work. Right. So the code that they write is the following, right? So they take the value of the counter, compute the remainder after dividing by 2, and then compare the value to 1. Right? And so if after dividing the value of the counter by 2 and you get 1, then they say, well, the value of the counter is odd. Right? Otherwise it's even. So if you look at what the counter class says for its value, right? It says that the value is always 0 or greater. Right? So you can create any counter that you want, right? And pass that counter to that method, and that method will always pass its unit test. So this method is provably correct until someone comes along and creates a subclass of counter that doesn't follow its invariance. Right? So someone comes along and say, hey, I want a counter that counts down or can count both up and down. And I'm going to call it descending counter. Okay. So when they implement descending counter, they say, well, I can count down to the negative, to the most negative value. Right. So we go down to min value now, and then wrap around back to max value if we try to count past min value. Right. So just like a regular counter behaves when you count past max value. All right. So this class is dead easy to implement. Right? It's just extending counter. Okay. So this particular counter only counts down, so its advanced method gets overridden, right? And now the value goes down every time you call advance, right? Otherwise, there's nothing to write. And so everything is done correctly here in terms of the mechanics of implementing inheritance, right? We've got our class, we extend our superclass, right? We call our superclass constructors here, right? Override the advanced method to get the behavior that we want, right? And now you run into a problem, right? So now, you hand your class out to the rest of the world, people start using it, right? And now you start getting complaints that when you pass one of these counters to isOdd, it fails, right? Why does it fail? So if you go back and look at isOdd, right? If you have a negative value and you take the remainder after dividing by 2, you get a -1, right? If the counter is odd and negative, right? And so this returns true. So a counter whose value is say -3 apparently has an even value. And so yeah, so now this method, which was provably correct, is now incorrect when it's passed a descending counter. which is not a place you want, is not a good position to be in. Right. Now, you can argue that whoever wrote is odd wrote this incorrectly. You can easily fix this, right? Just return, take the remainder after dividing by 2 and check if it's not equal to 0. Right. And now the descending counter will also work. Right. But whoever wrote this method, they are justified in writing that line of code there. Right. It's correct as far as counter is concerned. Right. And they're writing the method assuming that anybody who passes in a counter is going to pass in something whose value is not negative. Right? Someone comes along, makes a counter that breaks the class invariant of counter, and now code that was correct suddenly breaks. Okay, so does that mean that your class, your subclasses have to have the exact same invariant as the superclass? The answer is no. Right? The subclasses can change the invariants that are inherited from its ancestors, right? But when they change the invariants, right, the modified invariants must still satisfy the inherited invariant, right? So the inherited invariant here is that the value of the counter is positive. So if you remember back when we were talking about creating the counter class. Oh, sorry, we did this with the range, not with the counter. You can make a range counter that counts between 2 values. So instead of going between 0 and integer max value, you can create a range counter that counts between some minimum value and some maximum value. As long as the range of the minimum and maximum value is non-negative, right, that still satisfies the counter invariant, right? The value of a range counter will always be between min and max, right? So that becomes its invariant. Right, and min is greater than or equal to 0. Right, so now your range counter has a different invariant, but it still satisfies the ancestor class invariance. Right, so you are allowed to change invariants, but your modified invariants have to be compatible with the inherited ones. So here we now have a description of the invariant. Right, so the counter keeps count between min and max, where min is greater than 0 and max is greater than the min. Right, easy to implement again. Right. This is implementing this class, though. This is an example of where you have to add new fields. Right. So the counter only has one field called value. Right. The range counter now needs to also know what its min and max value are. So you have to add new fields here. So you would add a min, you would add a max, but you would not repeat the value field. Right, the value field still belongs to the counterpart of the ranged counter. Okay, so for the method or constructor preconditions and postconditions, I'm going to use this class called shape, which we haven't seen yet. It's described in that notebook there if you want to read about it. And so shape is a new type of class that we haven't seen before. So it's what's called an abstract class. Right? And so it's the superclass for all 2D shapes that I'm going to talk about today. Okay, so the shape class is marked as being abstract. Where is it? Here. Right? So when the shape class is declared, right, the keyword abstract appears. Right? So an abstract class is a class that that the programmer does not use to make objects directly. Right? So no one can come along and write shape S equals new shape. Right? That's not the purpose of the shape class. Right? So the word abstract, if you look at its dictionary meaning, it means existing only in the mind. Right? So the shape class is the idea or the general idea of a 2D shape. Right? To actually make a shape object, you have to subclass shape and create classes that represent actual shapes. So rectangle or triangle or circle or something like that. Right? So if I can't actually use this class to make objects, what is its purpose? Right? So the purpose of an abstract class is to serve as the superclass in some kind of inheritance hierarchy. Right? So in other words, it contains all of the common stuff that shapes should have. Right? So all of the methods that are common to two-dimensional shapes are going to go into the shape class. And all of the fields that are common to two-dimensional shapes are also going to go in the shape class. Right? Now, when someone wants to make an object of type shape, they first create a class. That class inherits all of the methods and fields belonging to shape, right? And now they just extend the class to make a shape of their choosing. So in a UML class diagram, it looks the exact same as a regular class, except the name is in italics. Right? And so if you ever see anything in italics in a UML diagram, that's probably indicating an interface or an abstract class. I believe correctly, it's only an abstract class. Okay, so what's inside the shape class? So remember, it's everything that's common to our two-dimensional shapes. Right? So we have some invariants here, right? So our shape class can only represent finite shapes having a finite dimensions. Right? So all shapes have a minimum, the width and height have a minimum value of 1 unit and a maximum value of 100 units. All shapes have a width and a height, and you can imagine other fields as well, right? But this is sufficient for our purposes. Okay, so we have this method called width, right? Now, if you look at the invariant for shape, right, the width is always between 1 and 100. So the width method also promises to return a value that's between 1 and 100, right? Remember, when a method promises something about the return value, that's a post condition, right? So the post condition of width is that the return value is between 1 and 100. Here's a method called area upper bound. So the area upper bound method returns an upper bound on the area of the shape. So imagine you have some very complicated shape that has some very strange perimeter, right? You can imagine that it's very hard to calculate the true area of that shape, right? But it's very easy to give you an approximate estimate of the shape. You just draw a big rectangle around the shape and return that area. And so that's what this method does, right? So this method returns the upper bound on the area of the shape, right? It even tells you subclasses should override the method if they can provide a better upper bound. So for example, a rectangle can give you the exact area, right? Or a triangle can give you the exact area, or a circle can give you an exact area, right? So they should override area upper bound so that it actually returns a better upper bound on the area, right? But otherwise, every shape class inherits that method there, right? So the upper bound is the rectangle surrounding the object. Finally, there's a method called set dimensions, which changes the shape, right? So notice the first two don't change the shape, right? This one returns information about the shape. This one returns information about the shape. This one actually changes the dimensions of the shape, right? And it says specifically it changes both the width and the height of the shape to the specified dimensions, right? So after calling this method, assuming width and height are valid, your new size of the shape will have that width and that height. Right, that's at least what's being implied here by the contract with this method. Right, if the width or height are illegal, you get an exception. Right, so if the size of the shape is less than 1 or greater than 100, you have an exception is thrown. Right. Okay, so all of these methods have some sort of post condition or precondition. Here, the precondition for set dimensions are that the width and the height are between 1 and 100. Okay, so using that shape class, right? So we don't have any types of shapes yet, right? We don't have rectangles, circles, or squares or anything like that. And the class is abstract. So we don't even have shape objects, right? We're not in the position to make shape objects, but you can go ahead and write all sorts of code involving shapes, right? As long as you use only the methods that are in shape, the compiler will happily compile that code. Right? So for example, you can write a method that changes the size of a shape to some random value. Right? If you test this method, it will work with any shape that you can imagine, assuming that the shape obeys all of the class invariants and obeys all of the method preconditions for this method. Right. So someone makes a utility class. Right. They make a method called random scale that takes in any shape object. Now, the way this method works is it randomly changes the size of the object by a small amount. Right. So over here, I've got this value 0.01 minus 0.005. Right. And that's multiplied by some random value between 0 and 1. Right. So the value of this thing inside the parentheses is a value that's between 0.095 and 1 times. So if it's 0, then it's 1 plus some random value here. This random value is between minus 0.005 and plus 0.005. Right? So if you interpret that as a percent, this is scaling the width by plus or minus by up to plus or minus 0.5%. Right? And same with the height. Right? So the new height of the object will be scaled plus or minus 0.5%. Now, before we're going to call set dimensions to set the size of the shape to the new width and height. Right? Now, before you do that, you have to make sure that the new width and height satisfy the preconditions for set dimensions. Right? So we have to make sure that the new width is greater than 1, greater than or equal to 1, and less than or equal to 100. And same with the height. As long as those conditions are true, we can safely call set dimensions. Right? And so this method here will always do exactly what it says it will do. Right? It will always randomly change the size of the shape, changing the size of the shape afterwards. Right? Perhaps it's random, so perhaps the size of the shape stays the same. Right? But that code as written is correct, right? Given the description of the shape. Okay, so now someone comes along and says, well, look, I want to use your shape class, so I'm going to go ahead and make a rectangle. Right? And then someone else comes along and says, well, look, you've got a rectangle. I want to use that code there and make a square out of that rectangle. Right? The argument being, well, a square is just a rectangle whose width and height are both the same. Right? You should recognize that by now this is going to be a problem. Okay, so how does substitutability come into play when you start to have subclasses? Right. Okay, so any method that has a precondition is now going to affect all of the subclasses. Right. So shape has a precondition. The set dimensions method in shape has preconditions on the parameters. Any subclass that tries to override set dimensions, right, when they override it, that method must accept all of the parameter values that are accepted by the ancestor class version of set dimensions. Right. So in other words, if you override set dimensions, right, then it should accept all values between 1 and 100, right? And it should throw an exception if the values are outside of that range. Okay, so square now has a problem, right? So when you implement square, right, whoever's implementing square looks and says, hey, there's a set dimensions here method that says it changes both the width and the height. And I can't do that for a square, right? Because a square has the width and height are not independent. Right? And so they say, well, I can deal with this by throwing an exception if someone calls this method and passes in an unequal width and height. Right? So assuming someone passes in a valid width and height, we now need to change the size of the square. Right? So how do you change the size of the square? You call the superclass version of the method to change the size of the square. Right? So to call the superclass version of the method, right, you put the keyword super in front of the method call. Right? So the keyword super inside of a subclass method is a reference to the superclass object. Right? So super.setDimensions calls in this case, the rectangle version of set dimensions. The rectangle version of set dimensions probably doesn't override set dimensions, so it ends up calling the shape version of set dimensions, right? And this changes the width and height of the, in this case, the square to the specified width and height. Right? But notice what's happened here, right? Whoever implemented square has stuck in an extra precondition on the method, right? They've put in the precondition that the width and height must be equal. And so now what happens when you call random scale and you pass in a square? Right? Well, the width gets chosen to some random value. The height gets chosen to some random value, right? almost near certainty, the new width and height are not equal, right? If you get past that if statement there, so in other words, if the new size and shape of the height, so if the new width and height are equal and they're between 1 and 100, it calls set dimensions, right? Now remember how this works, right? Which version of set dimensions gets called? Right. So first of all, can we call set dimensions? The answer is yes, because this is a shape object, right? And shape says there is a set dimension method. Which version of the method gets called? It's the runtime type or the actual type of the object that you passed in. So if you pass in a square here, it's the square version of set dimensions that gets called, right? If the width and height are different, and they almost certainly are, this now throws an exception, right? Which breaks the implementation of random scale, right? A method which never used to throw an exception and never advertised that it would throw an exception now throws an exception when you pass a square. Yeah. Yeah. Oh, here. No, you can still. Oh, no. Shape can still have constructors, right? It needs a constructor to to initialize the fields. You just can't. So the programmer can't make a shape object. So the programmer can't come along and say shape equals new shape, right? So if you try to write that, the compiler will flag that as an error. It'll say you're trying to initialize or trying to create an object of abstract type, right? So what can you use this class for? Well, you can subclass this, right? So I can make a rectangle or a circle, for example, right? So circle extends shape, right? It's the circle object that needs the shape constructor because it needs to initialize its superclass part, right? So the programmer cannot directly make a shape object, but subclasses can still call the shape constructor, right? But the only way they can call it is with the super keyword. Okay, so this doesn't work, right? Or at least it doesn't work if you pass a square to that random scale method, right? It might work if you never pass a square to the random scale method, right? But any method that is relying on the shape version of set dimensions, which says that the width and height get changed independently, when you pass it a square, you will likely get undesired behavior. Okay, so when you override a method in a subclass, it's often very convenient to call the superclass version of the method, right? And this is what the square version does, right? I need to change the actual size of the shape, right? I could write this width equals width and this height equals height, but there's already a method that does that for me, and it's called set dimensions, right? So I should probably use that method instead. Right. So when you're in the situation where the subclass wants to call the superclass version of the method, use the keyword super, followed by the period, followed by the method name to call the method. Right. So when you're in the subclass version of set dimensions and you would like to call the superclass version of set dimensions, that's what the super keyword is used for. Okay, so this method here is incorrect. We added a new precondition to the method that the shape version of the method doesn't have. So you can't do that. Right? Does that mean you cannot change the preconditions on a method that you inherit from a superclass? The answer is no. You can change the preconditions, right? But what you can't do is you can never add extra conditions, and you cannot strengthen any existing conditions, right? What you can do, though, is you can remove preconditions that you've inherited, and you can weaken constraints on the parameter values that you inherited, right? So remember the constraint on the width and height that we inherited for set dimensions that we inherited from shape is that the width and height must be between 1 and 100, right? And if it's not, it throws an exception. There's nothing stopping you from creating a new class, overriding the method so that set dimensions takes in any width and any height, right? When it changes the size of the shape, it still has to make sure it's between 1 and 100. right? But it can now accept inputs that are outside of the valid range, right? So for example, someone could come along and whoever implemented rectangle, right, can say there are no constraints on the width and height that you pass into this method, right? Instead, what I'm going to do is if you pass in a value that's less than 1, I'm going to change that value to min length. And if you pass in a value that's greater than 100, I'm going to change that value to max length. But I'm not going to throw an exception. Okay. So how does this work? So you just make sure, so you given the width, right? You make sure that the width is at least equal to min length, right? You could use an if statement here, but it's easier to use math.max, right? So max returns the larger of 2 values, right? So you call math.max, you pass in the passed in width and min length, right? If width is less than min length, you end up with a width equal to min length, right? And you do the same thing with the height, right? Once you've made sure that the height, width and height are at least equal to min length, you now make sure that they're no greater than max length, right? And so there you use min to deal with that problem, right? So you call min with width and max length, right? If the width is greater than max length, you just end up with max length, right? And so once you get past those 4 lines there, you know that the width and height are between 1 and 100. And now you just go ahead and set this width to width and this height to height, right? Now there's no exception thrown by set dimensions for a rectangle, right? But that's fine, right? Any values that the superclass accepted for width and height, right? This version of set dimensions also accepts. Right? And then it sets the width and height to the appropriate values, right? So you can change the preconditions on an inherited method, right? But any value that's accepted for width and height in the superclass must also be accepted in the subclass. Right, so that's what happens with preconditions. So we know what happens with invariance in inheritance. We know what happens to preconditions in inheritance. Now, what about the postconditions? Right, so remember the postconditions are the conditions that the method guarantees will be true after the method finishes running. Right, so for example, if the superclass version of the method promises something about its return value, and a subclass overrides that method, right? Then however it overrides the method, the subclass version of the method must also satisfy the promise of the superclass. Right? So the width and the height methods in shape, they always promise to return a value between 1 and 100. Right? So that's their post condition. Okay, so given the method width and height, somebody can come along, write a method using the contracts that they got from shape, right? And this particular method is going to normalize the width of the shape, right? And so normalizing something or quantity is a pretty common operation in science and engineering. So basically, when you normalize something, you want to set its value to 1. Right? So for normalizing the width, we want to scale the size of the shape so that its width is equal to 1, right? As long as the width is currently greater than 1. Sorry, as long as the width is currently, yes, as long as the width is currently greater than 1. Right? So in other words, if it's less than 1, we're not going to bother to scale it back. We're not going to bother to scale it up. There's an extra constraint here that we have to be careful about. Right? You can do the same thing with the height or the area or anything else. Well, you can try to do the same thing for the area. It's not going to work for this particular class, right? But you can normalize any quantity, and it's very common to do so, right? So in other words, I want to work with shapes so that their widths are always between 0 and 1. Right? Now you can do this, right? So it's easy to do. Just basically what we're going to do is we're going to divide by the width, right? So we're going to take the dimensions of the shape and divide both the height and the width by width. That'll set the width to 1. That'll set the height to some value. And the size, the aspect ratio of the shape doesn't change, right? So the shape of the shape doesn't change, right? It doesn't get stretched or it doesn't get stretched or compressed in any way, right? Its size just changes, right? So the width can't be 0 and the height has to be greater than the width in this particular case, right? Because we're going to divide the height by the width. If the height's less than the width, then the height becomes less than 1, and that doesn't satisfy the invariance of our class. Right, so we have to be a little bit careful about that. Right. If you're careful about this, then you can write this method and it will be provably correct. Right, it's pretty easy to write. Right, so if the height is less than the width, then we're not going to bother scaling the shape in this case, right? Because that's going to cause the height to become less than 1, which we don't want. Right. Otherwise, we're going to take the height divided by the width. This is safe because we know that the width method promises to return a value between 1 and 100. Right, so it's never 0, so I don't have to worry about dividing by 0. Right. You then set the width to 1. Right, and now I change both the width and height of the shape using set dimensions. Right, this will never throw an exception, right? Because the width and height, I know the width is 1. I know the height is greater than 1 back here. Right, so that'll never throw an exception. So this should be correct. Right? It's provably correct, given the description of the methods that we got from shape. Okay, so someone comes along and they make a class called vertical line, so V line. Right, and whoever makes the class says, hey, look, this is just a line. It has no width. Right, so it has a width of 0, which is bad 2 times. Right, so it's bad, number 1, because it breaks an inherited class invariant. Right, it's bad because it's bad in the second way because now width returns 0, right, which breaks its post condition. Right, the post condition for width in the shape class says that the width is always between 1 and the returned value is always between 1 and 100. Right, so whoever wrote this method here is relying on that post condition. Right, but again, it's very easy to go ahead and break, go ahead and write this class. Right, so what's a vertical line? Well, the vertical line is a line that has a width of 0. Right. What does width do? Well, it returns 0. Right. That's right. So this is a problem that breaks the class invariant. That's a problem there that breaks the post condition on the method. So what happens when you call normalized width with a vertical line? Right. The width comes in, so the height is the height. Oh, actually, this will probably actually survive. I shouldn't have put that if statement in. Anyway, this now survives because I stuck that if statement in before class. If the if statement wasn't there, this would end up dividing by 0, and that would break. Right. So this method is not going to do anything. I have to remember to fix that. Okay. That's bad. That's bad. Okay, so that's my mistake there. Oops. Right. Okay, so the previous version of normalized width would fail when you pass it a vertical line instance, right? It would end up dividing the height of the shape by 0. And so you now end up with a shape whose height is infinite in length. Okay, so you can't, so that was an example where you have a post condition that was modified incorrectly, right? So the question is can you, does that mean you can never modify a post condition? And the answer is no, that's not true at all, right? So class is allowed to return a different value in an overridden method, right? Compared to its superclass, compared to the superclass version of the method, right? As long as you're still satisfying the contracts of the superclass, right? So for example, you can cook up a triangle class, right? And you can override area upper bound so that it returns the exact area of the triangle, right? So for the exact area of a triangle is just 1/2 the width times the height, right? That's a different value than the value returned by the shape version of area upper bound, right? In fact, it's exactly 1/2 the area, right? But this is fine, right? You can return a different value from a superclass version of method, right? As long as the description of the method is, as long as the post condition of the method is still satisfied, right? The post condition of area upper bound inherited from shape is that you get an upper bound on the area of the shape, right? Now you get the true area, but that is still an upper bound on the area of the shape. So this is fine. And finally, what happens with that? We have a mutator method. So we have a method that changes the dimensions of the shape, right? So that one has different post conditions. So if a superclass method promises to change the state of an object in a particular way, right, your subclass overrides the method, right? The subclass version of the method must change the state of the object in a way that satisfies the promises of the superclass. Right. So back in Square, right, we had that method called set dimensions, right? We know that the Square version of set dimensions is broken because it's not satisfying the post conditions of the set dimensions method from shape, right? Can you fix set dimensions, right? Well, let's try to fix set dimensions. Right. So the previous version threw an exception when the height and width were not the same, right? This version of set dimensions, right, simply ignores the passed in height. Right. So you passed in a width and a height, and now it just sets the dimensions to whatever the width was that was passed in. That guarantees that the square is still the square, right? But does that satisfy the post conditions in the superclass? The answer is no. Right. The superclass version of the method says the width changes to that and the height changes to that as long as the width and height are between 1 and 100. Right. So this version of the method does not satisfy the superclass's post conditions. Right. Now, is this bad? Well, it could be. Right. So when would this be bad? So this would be bad if someone writes a method that uses set dimensions to change the shape, to change the size of the shape so that it fits inside of some other shape, or it fits into it fits into some space that is size constrained. Right. So here, if Square only uses the width to determine the new shape, the new size of the shape, right? The scaled square may not fit into the area that the other programmer hasn't. The other programmer wants the shape to fit into. Right. They're using both the width and the height to determine can the shape fit into this space, right? But Square is only using the width to actually change the size of the shape. So that doesn't work either, right? You can still come up with situations where this breaks code that was written using the shape contracts. Okay, so can we fix Square at all? So we're going to try to fix Square one more time, right? So now set dimensions does nothing, right? And the creator of the Square class says, look, to change the size of the square, don't use set dimensions, use set length instead, right? So set length, this is now a new method. So everything about preconditions and postconditions goes out the window, right? Because that they no longer apply, right? So now set length can define its own preconditions and postconditions, right? So presumably length is between 1 and 100, right? Presumably the postconditions are you get a new square whose size is length, right? So this method is correct, right? But this method is now broken, right? Someone who writes code, assuming set dimensions actually changes the size of the shape, right? Now when you pass it a square, the size doesn't change, and whatever code was written no longer works the way it's supposed to, right? So it turns out in this case, there is no way to fix square so that it is still substitutable for shape, right? Not if you do it this way anyway, right? So our shape hierarchy, the way it was designed, can't actually represent squares, right? Because the method set dimensions says that when it changes the size of the shape, both the width and height change to the passed in values, right? Same thing applies to circle, right? You can't implement circle because there's this set dimensions method in shape, right? There's no way to override set dimensions properly so that a circle remains a circle after calling this method. And so the problem here is in the design of the shape class itself, right? Whoever implemented shape has to probably go back and reconsider what they wrote when they described what set dimensions should do. All right, so that's we are done. So I think that wraps up the discussion for inheritance in this particular version of the course. There is more to say. So I didn't tell you what happens when you have static methods in inheritance, but that's okay. I think what we're going to do is we're going to move on to the fourth part of the course after this. And so the fourth part of the course talks about generics in Java and how you implement them. Right. And so we'll talk about that in the next class. Okay. That's it. We're done for today. Where did this go?